In the following video demonstration, we will programmatically build a simple data lake on AWS using Apache Airflow. Since we are on AWS, we will be using the fully managed Amazon Managed Workflows for Apache Airflow, or Amazon MWAA for short. Using Airflow to automate a number of AWS services, we will move data from 3 separate data sources into our Amazon S3-based data lake. Once in the data lake, we will use Airflow to perform ETL, or more accurately, ELT, on the raw data, preparing it for data analytics and machine learning. Agenda. First, we will define what is a data lake. Then, I will describe the data set we will be using in the demonstration. Next, I will review the architecture used in the demonstration. Then, I will let you know where all the open source code is. And finally, we'll spend the majority of our time in the actual demonstration. What is a data lake? I have 2 definitions of a data lake, one from Databricks and one from AWS. I'll read both to you. First, from Databricks. A data lake is a central location that holds a large amount of data in its native raw format. Compared to a hierarchical data warehouse which stores data in files and folders, a data lake uses a flat architecture and object storage to store the data. Now a definition from AWS. A centralized repository that allows you to store all your structured and unstructured data at any scale. You can store your data as is without having to first structure the data and run different types of analytics, from dashboards and visualizations to big data processing, real-time analytics, and machine learning to better guide your decisions. Dataset. The dataset for our demonstration is a ticket database. The ticket database is provided free by AWS. The ticket database represents an e-commerce platform. It brings together buyers and sellers of tickets to entertainment events. The ticket database was originally designed to demonstrate Amazon Redshift Cloud Data Warehouse, but we will be using it to build our data lake. The ticket database is a small database consisting of 7 tables, 2 fact and 5 dimension tables. The tables include categories, events, venues, users, listings, sales, and dates. The link to the ticket database is shown on the screen. Here is a schema diagram showing the relationship between the 7 ticket database tables. A data lake typically contains data from multiple data sources, each with different data storage formats, protocols, and connection methods. To simulate this, I have split the ticket database into 3 separate data sources. Each data source represents a different enterprise system. To simulate these 3 enterprise system data sources, I've created 3 different Amazon RDS instances, each using a different database engine. The categories, events, and venues are all contained in an Amazon RDS for PostgreSQL database. This represents a third-party SaaS provider. The listings, sales, and dates are all contained in an Amazon RDS for MySQL instance. These 3 tables represent a commercial off-the-shelf e-commerce platform. Finally, the users are contained in an Amazon RDS for Microsoft SQL Server. These represent a custom CRM system. Architecture. The following AWS services are used in the demonstration. I've also listed possible alternatives to these services: Amazon Simple Storage Service, or Amazon S3, AWS Glue Studio, AWS Glue Data Catalog, AWS Glue Crawlers, AWS Glue Jobs, Amazon Athena, and finally, Amazon Managed Workflows for Apache Airflow, or Amazon MWAA. On the screen, you see a diagram which represents the architecture for our demonstration. In the demonstration, we'll use a series of Apache Airflow directed acyclic graphs, or DAGs, to programmatically construct our data lake. Each step in the diagram represents an Airflow DAG containing multiple tasks. The data lake will be organized based on a pattern of raw or bronze data, refined, aka silver data, and aggregated or gold data, as popularized by Databricks. In step 1, we will catalog the data in our 3 data sources running on Amazon RDS to our AWS Glue Data Catalog. The AWS Glue Data Catalog is a Hive-compatible metastore which stores the metadata, schema, and partition information about the data in our data sources and in our data lake. In step 2, we will move the data from our data sources into the raw or bronze area of our data lake using a series of AWS Glue jobs. The AWS Glue jobs use Apache Spark. We will store the data in Apache Avro format. Avro is a row-based binary file format. The raw or bronze data will also be cataloged in the same AWS Glue Data Catalog. In step 3, we will cleanse, augment, and prepare the data for data analytics, again using a series of AWS Glue jobs based on Apache Spark. The data will be written to a refined or silver area of our data lake in Apache Parquet format. Parquet is a columnar format commonly used to store data in a data lake. Once again, the refined or silver data will also be cataloged in the same AWS Glue data catalog. Lastly, in step 4, we use Amazon Athena, AWS's ad hoc query engine based on Presto, to produce aggregate datasets, joining together several datasets in the refined area of our data lake. We will produce multiple views of the data and partition the data based on the most common query and filtering patterns of our end users. Those aggregate datasets will be written back to the gold or aggregated area of our data lake as partitioned Apache Parquet files. As I mentioned, each step in the architectural diagram represents an Airflow DAG or directed acyclic graph containing multiple tasks. Here we see the DAGs in the Airflow UI that we will be using in the demonstration. Since this is a simple demonstration, we can't possibly incorporate all the processes that go into building and managing a typical production-ready data lake. However, since these are critically important items, I want to quickly review what is out of scope before continuing. Change data capture, or CDC, handling changes to the system of record. Transactional storage layer, managing changes to the source data. Streaming data, data continuously generated by different data sources. Fine-grained authorization, database, table, column, and row level access. Data lineage, data's life cycle as it flows from source to consumption. Data discovery and inspection, scanning data for sensitive or unexpected content, such as PII. Data ops, automating the testing, deployment, and job execution of resources related to our data lake. Infrastructure as code, infrastructure provisioning automation as it relates to our data lake. Data warehousing, and data warehousing in combination with our data lake, also known as the lakehouse architecture. Data lake storage tiering, archival, and backup. Source code. All of the source code for this demonstration is open sourced and available on GitHub at github.com/Gary Stafford/ticket-data-lake-demo. The GitHub repository contains my notes, the Airflow DAGs, all the SQL statements, and the raw ticket data. We will now jump into the demonstration. I will start by reviewing the resources that I have already created on AWS in advance. First, I provisioned a small development-grade Amazon managed workflow for Apache Airflow or Amazon MWAA environment. I've also configured a number of environment variables and loaded the DAGs we'll be using for the demonstration into an Amazon S3 bucket, which is accessible by Airflow. If I switch over to the Apache Airflow UI, we have DAGs that correspond to each step in the workflow that we discussed earlier. So I have DAGs for step 1, step 2, step 3, and step 4. I also have a DAG that I'll demonstrate at the end that will run all 4 of these individual DAGs as a single DAG. So we're able to execute all of the tasks required to build our data lake using a single DAG versus individual DAGs. I'll be demonstrating both of those. I also have a preliminary DAG, 00 DAG, which will clean up any existing resources from previous runs of the demonstration and prepare the environment for the new demonstration. One thing to note, you'll notice in my environment the current version of Airflow for Amazon MWAA, the 2.x version is 2.0.2. So 2.0.2 is the current Airflow version available through Amazon MWAA. The current stable version of Apache Airflow is 2.2.1. If you're working on developing DAGs for Amazon MWAA and you're working in your own local development environment, make sure that you're using the proper version. So again, that's 2.0.2 currently when you develop your DAGs if you want to ensure that they're going to run right on MWAA. Next, I've created 3 Amazon RDS databases and imported the ticket data into the appropriate databases, into the appropriate tables based on the chart I showed in the introduction. So you can see here on my screen, I have 3 Amazon RDS instances. I have an Amazon SQL Server Express edition. I have a MySQL Community edition, and I have a PostgreSQL edition. These will simulate our 3 enterprise data sources as we build our data lake. I also have 3 AWS Glue connections. These 3 JDBC connections contain the connection information required to securely connect from AWS Glue to the 3 data sources, the PostgreSQL, MySQL, and Microsoft SQL Server databases where the ticket data is located. Next, I have 3 AWS Glue crawlers. Using the 3 AWS Glue connections I just showed, the crawlers will extract schema and metadata information from the tables within the 3 data sources. The crawlers will create a series of 7 tables in our AWS Glue data catalog, representing the 7 tables from our 3 data sources. Those tables will contain schema and metadata information about the data located in our 3 data sources. Lastly, I have a series of 14 AWS Glue Studio jobs. The first set of 7 jobs will extract the data from the 3 data sources using the information in the AWS Glue data catalog. The jobs will write the data into the raw or bronze area of our data lake as Apache Avro format. The second set of jobs will perform basic ETL on the bronze or Avro data, cleaning it up for future analysis and writing it into a refined or silver area of the data lake as compressed Apache Parquet format. As part of the AWS Glue Studio jobs, a new table representing the new bronze and silver data in the data lake will also be written to the AWS Glue data catalog. So we're ready to begin our demonstration. I'll run DAG0 first. That will clean up our environment. It will delete any existing artifacts from previous runs of the demonstration and prepare it for this demonstration. It will also create an empty AWS Glue data catalog, which we'll use to build out all of the schema and metadata information about our data sources and the data in our data lake. The first DAG, DAG0, is using the bash operator. So instead of using specific AWS operators, I'm going to be using the bash operator to start. And we're going to be using the AWS CLI command. So things like AWS S3 remove, AWS S3 API list objects, AWS Glue delete database, and AWS Glue create database. We're going to be using the bash operator and executing these AWS CLI commands within this DAG. This DAG again will clean up any existing S3 objects. It will delete any existing AWS Glue data catalogs associated with the demo, and it will create a fresh catalog with no tables in it, which will be the basis for this demonstration. If I flip back over to the Airflow UI, we can see the DAGs here, and I'm going to go ahead and kick that DAG off. So I'll start that DAG running. So we've now triggered that DAG. It should start in a moment. If we want, we can go in and take a look at it. So let's first look at the graph. Since it's a directed acyclic graph, we'll look at the graph view. And we can see that in parallel, we're both deleting the existing AWS Glue data catalog and we're creating a brand new catalog. So if a catalog exists, it will delete it and it will create a new one. Also, within our AWS data lake, within the Amazon S3 bucket, we're going to go ahead and delete any existing objects. So if we run this demo before, I might have some existing objects. I've gone ahead and cleaned those up. So it looks like our DAG is almost finished. It's run through everything. If you're not familiar with the Airflow UI, this is the Airflow UI. We're looking again at DAG0. We can see a tree view. We can see previous runs. So I've run this a few times. The farthest to the right dots are the current run, and the fact that they're all green is good. That means that our DAG completed successfully. We can see a graph view. So this is the directed acyclic graph view of our DAG. And again, we can see that we have two tasks running in parallel. And we can see other things like the duration of the tasks, details, and we can also see the code. This code is the same code that we saw in our UI. So if you've uploaded the DAG to S3, there is a slight delay between the time it's uploaded to S3 and the time that it's available through Airflow to be able to execute. So it's always good to check the code and make sure that you have the latest version. We completed step 0 and we're ready to continue with the demonstration. Next, I'm going to run the first DAG or DAG1. Again, if we flip back to our architectural diagram, the first step was to use an AWS Glue crawler, actually a series of 3 crawlers, one that corresponds to each one of our 3 data sources, to crawl the data source, extract the information about our ticket resources, and populate our AWS Glue data catalog. So what I would expect to happen when I run DAG1 is that our 3 existing AWS Glue crawlers will start. They will extract metadata and schema information from our 3 data sources, from our PostgreSQL, MySQL, and SQL Server data sources, and it will place that metadata and schema information in our AWS Glue data catalog in 7 tables. So when the DAG finishes, I expect to have 7 tables of schema and metadata information in my AWS Glue data catalog, which corresponds to the 7 ticket tables, which are distributed across our 3 data sources. So let's go ahead and start that DAG. Again, I'm going to go to the Airflow UI. We see that we have the DAGs associated with our demo. This time I'll go into DAG1, and let's take a look at it before we start it. So again, we can see the tree view. Let me switch over to the graph view, or the directed acyclic graph view. So you can see here that we have our 3 crawlers. We're going to kick those off in parallel. They're not dependent on each other, which means we can run all 3 of those in parallel. And when we're all done, I'm going to list the tables and the logs just to make sure that our 7 tables were created. So let's go ahead and start that. We'll trigger that DAG. And we can see here by the light green dot that it is started. Again, this is the latest run to the far right. We've run it a few times successfully. I've tested it and I know that it should work. If we go to the graph view, you can see that we have different modes. So the color of the boxes indicated stage: queued, running, success, failed, retry, rescheduled, skipped, scheduled, etc. So I also have auto refresh turned on. So as each one of these boxes or each one of these tasks are completed, the color should change to a dark green. We're going to go ahead and let this run. I expect that those crawlers will probably take anywhere from 3 to 5 minutes to run. So I'll pause the video. Once they're complete, we'll take a look at the DAG and we'll also take a look at the results to make sure that the DAG executed correctly and that we're able to extract the schema and metadata information from our 3 data sources and put those into our AWS Glue data catalog. So we can see that our crawlers are starting to finish. Let me switch over to the AWS Glue console. And in fact, we can see that our crawlers are beginning to finish. Looks like one of them is stopping, 2 of them have already completed. Notice on the far right that it indicates that a total of 7 tables were created in our brand new AWS Glue data catalog. So as those are finishing, let me look at our AWS Glue data catalog. So we can in fact see that we have 7 tables created. We can see the classification, MySQL, PostgreSQL, or MS SQL. We can see the location, so their database and table name or database schema and table name depending on the database engine. And we can see that they're all in our ticket_demo AWS Glue data catalog. So that's good. That means that our first DAG ran successfully, that all 3 crawlers were executed successfully, and we created 7 tables in our AWS Glue data catalog. Again, we haven't moved any data out of our data sources. DAG1 simply executed 3 AWS Glue crawlers. Those crawlers crawled the 3 data sources, extracted metadata and schema information from those 3 databases, and placed that in our AWS Glue data catalog. We can see that our DAG is now completed successfully. All 4 of the tasks were successful as indicated by the dark green outline on each task or each box. Let's go ahead and take a look at one of these. There's logs associated with each one of these tasks. So I'll go into the logs for one of the crawlers. And we can see normal outputs. So we see that the crawler was kicked off and that the crawler completed successfully. If I go back to the graph view for a minute, we remember that the last task that we ran was to list the glue tables. So after the crawlers completed, we expected 7 tables in our AWS Glue data catalog. So one of the tasks that I created was to actually go in and list those tables. So let's take a look at the logs and see if we're able to list those tables. And in fact, we were. So do you remember when we went into our AWS Glue data catalog, once our crawlers completed, we saw the 7 tables. I've also listed those in the logs, so we can see the same 7 tables listed here. That means that we were successful. Now that we've completed DAG1, we've extracted the metadata and schema information from our 3 data sources, we're ready to go ahead and run DAG2. Let me open that in the IDE. So DAG2 runs a series of 7 tasks, AWS Glue job operators. These AWS Glue job operators will execute 7 different AWS Glue jobs, or Spark jobs. Each one of those Spark jobs is associated with a particular table spread across our 3 data sources. These Spark jobs will extract the data from the data sources and will write that into the raw or bronze area of our data lake in Apache Avro format. If I switch over to the graph view for this DAG, you can see that we're going to run all of those in parallel. Since these tasks are independent of one another, in order to save time, we can execute all 7 jobs in parallel. Once these jobs have all completed successfully, we'll list out the glue tables. So I would expect to see 7 more tables in our AWS Glue data catalog with the raw _ prefix, which indicates the raw data in the raw or bronze area of our data lake. If I switch over to AWS Glue for a moment, let's just take a look at these jobs before we run them. You remember that I mentioned we have 14 jobs, 7 to take the data from our PostgreSQL, MySQL, and MS SQL databases, extract that data, and write it into our bronze or raw area of our data lake. We also have 7 additional jobs that will run later on that will take that bronze or raw data, refine it, augment it, cleanse it, and write that to the silver or refined area of our data lake. So we have the _refined jobs and the _raw jobs. We're going to be running the 7 _raw jobs next with DAG number 2. Let's take a look at one of these AWS Glue jobs. These jobs are fairly simple. They just have a source and a target. So taking the data from our 3 database engines and writing those into our data lake. Now, why would we want to do that? Why not just transform that data and put it directly into the silver section of our data lake? That's a question I get quite often. Because I want a record of the data unchanged in our data lake. So in addition to our system of record, I want to extract that data as is without any changes and write it into our data lake and save that off. So if I ever want to perform additional ETL, if I want to change the ETL or the transformation I'm performing on the data, I don't have to go back to the data source later on. I have a copy of that data and I'm able to retransform it from bronze to silver, from raw to refined. So all 7 AWS Glue jobs to extract the information from our 3 data sources and write those into the bronze or raw area of our data lake look very similar. The only difference is really the database engine. So the job I have on my screen is extracting the dates table from the MySQL database and writing that into the bronze or raw section of our data lake. If I were to look at the other 6 jobs, they would look very similar. The only difference being the source, which is the 3 different database engines that we're targeting, and the table within those sources that we're targeting. We're then writing those into the bronze area of our data lake. So you can see here, I have Avro format. I'm not using any compression. And then I'm writing that into this bucket in the data lake, into the ticket subdirectory or key, into the bronze area, and then by date. So we'll go ahead and start DAG 2. When this DAG completes, I would expect to have the 7 glue jobs complete successfully. We'll have 7 additional tables in our AWS Glue data catalog representing the raw data in our data lake. And within our Amazon S3 bucket, within our data lake, within the ticket directory, within the bronze subdirectory, we'll have 7 subdirectories containing Apache Avro format files, 1 or more files, which contain the data from those 7 tables that we extracted the data from in our 3 data sources. So let's go ahead and start this DAG. So I've triggered the DAG. That should take a few minutes to run. We can see here that the job's starting. So again, if we look on the far right of my screen, the green dot signifies that this run has started. If we go back to the graph view, again, we see that it's starting. Let me just make that a little smaller. So we can see that the 7 jobs are starting in parallel. If I switch back over to the AWS Glue Studio and we go to monitoring, we can actually watch these jobs. So we can see that there's 5 jobs running. Go back over and look at our DAG. We'll let that run, and when it's finished, we'll take a look at the results. At this point, we can see that all of the jobs have started and 3 of the jobs have completed. The other 4 are still running. Once they finish, we'll take a look at the results. So we can now see that the DAG completed successfully. All 7 AWS Glue jobs were run. Let's take a look at the final task. Again, we're going to list the tables. I'll go to the logs for that particular task. And I'd expect to see 7 new tables in our AWS Glue data catalog. So first, let's look at the log. So we do in fact have 7 tables with the raw underscore prefix. Let's switch back over to our AWS Glue data catalog. You can remember that after running DAG 1, we had 7 tables representing the 7 tables in our 3 data sources. If we refresh that, I now in fact have 14 tables. Let's filter by the classification of Avro. We in fact have 7 Avro tables. So you can see that we have 7 Avro tables. The location is our Amazon S3 based data lake. In the ticket key or ticket subdirectory, within there we now have a bronze directory. And within that we have a directory which represents each one of the 7 tables. Let's switch over to Amazon S3 and actually take a look at those files. So let me go into one of these tables. We have the link here, so I'm in the raw ticket public date table. This table contains a schema and metadata information about the dates table. If I go ahead and click on this link, this should take me to the Amazon S3 location where that data has been written. Those Apache Avro files have been written. So you can see I'm in Amazon S3. I'm within the bucket that I've created to be my data lake. I'm within the ticket bronze date directory. And I in fact see a series of 20 objects or 20 Apache Avro files. So all of the date information was extracted from the database, from the MySQL database, and it was written into the bronze area of our data lake. So that looks like it was successful. If I go back out now, I have the ticket directory. Within that I have bronze, and within that I have 7 subdirectories. Each one of those contain Avro files. Those Avro files, these 7 directories, represent the data that was in our 3 data sources. So now after completing DAG 2, we've extracted all the data that we wanted to extract from our 3 data sources, and we've written it into the raw or bronze area of our data lake. Let me go back to the Airflow UI. Let's go back to our DAGs. So the next DAG we're going to run is a very similar DAG to DAG 2. DAG 3 is almost identical. It also runs 7 AWS Glue jobs. The difference is these Glue jobs take the raw or bronze data. Each one of them perform particular ETL or ELT on that. It may remove fields. It may concatenate fields. It may change the type of certain fields. It may replace empty fields with null. The actual ETL really isn't important to this demonstration. It's more the fact that we're taking the raw data, we're cleansing it, we're augmenting it, we're preparing that data for data analytics. So we're taking that raw data and we're going to write it back into the silver or refined area of our data lake in a format which is more optimized for data analytics. The other thing that these jobs are doing is taking the raw or bronze data, which again is in Apache Avro format, and it's going to write that data back into the silver or refined area of our data lake as Apache Parquet. Apache Parquet is a columnar format data. It's much more efficient for performing analytics on. So we'll go ahead and start this DAG. Let me get that started. Again, this is going to kick off 7 jobs in parallel. Since there's no dependency across those jobs, we can start all 7 of those in parallel to save time. They should take 2 to 3 minutes to run. We can see that they're already starting. Let me switch back to my ID for a minute. We'll take a look at this DAG. Very similar DAG to DAG 2. So we're using the AWS glue job operator. We have 7 AWS glue job operator tasks that we're running. And then when we're all done again, we're just using the bash operator to list those tables in our AWS glue data catalog. We'll let this DAG run. Once this DAG completes, similar to DAG 2, we'll go ahead and take a look at the results and make sure that it did work properly. We can see the DAG is still running. We can see that 5 of the jobs have completed successfully. 2 of the jobs are still running. Again, once the DAG finishes, we'll take a look at the results. Okay, well, it looks like DAG number 3 completed successfully. Let's go ahead and take a look and see what the results are. First, let's look at the final task, the list glue tables task. Let's see that it actually listed out the tables that we expected to be created in our AWS glue data catalog. So if we take a look at the Airflow logs for that task, in fact, we do see 7 new tables with the refined underscore prefix. We'll go ahead and take a look and see if those are actually in our AWS glue data catalog, but so far this looks good. It looks like the DAG completed successfully. If we go back over to our AWS glue data catalog, let me go back out to tables. You recall that we started with 7 tables which represented the source data from our 3 data sources. We then created 7 more tables with the raw underscore prefix, which were in Apache Avro format, which represented the raw data in the bronze area of our data lake. You can see now that we have 21 tables. So in addition to the source underscore tables and the raw underscore tables, we now have refined underscore tables. Let's filter those down just to be able to look at those a little easier. So we'll filter by classification Parquet. And we do in fact see 7 Parquet tables with the refined underscore prefix. If we go back to Amazon S3, let me go into one of these tables. Let me click through the table into the location where the underlying data is located. Again, the table just represents the schema and metadata information and location of the actual data in Amazon S3. I've gone into the Amazon S3 bucket, into our data lake bucket, into the ticket silver user subdirectory or key path, key prefix. You can see again we have 20 objects. And now these 20 objects are not in Apache Avro format, they're in Apache Parquet format. So we have snappy compressed Apache Parquet files. And these files represent the refined or silver data. So we've taken the data, extracted it from our data sources, our databases. We've then taken that raw data that we extracted. We've performed ETL on it. We've augmented it. We've cleansed it. We've corrected any anomalies in the data. And we've written that data back to Apache Parquet format. So this data is available to be used by our data analysts and data scientists. They could start using this refined data. We're going to go ahead and refine this even further. We're going to create some final aggregated data sets for use in the gold or aggregated area of our data set. But this silver data could start being used by our data scientists and data analysts as long as they understand how to use the data and how to aggregate or join the different data sets together. Let me go back to our diagram for a minute just to remind us where we are. So we've ran 3 DAGs. We ran 4 DAGs. DAG 0 cleaned up our environment. DAG 1 extracted the information from our data sources, the schema metadata information, and wrote that into our AWS glue data catalog. Step through then extracted that data from our data sources using the information in our AWS glue data catalog and wrote that into the bronze or raw area of our data lake. In step 3, we ran our AWS Glue Spark jobs, which took the raw or bronze data, performed ETL on it, and wrote that into the silver or refined area of our data lake. Our 4th and final step is going to be to use Amazon Athena, which is AWS's ad hoc query engine based on Presto. We're going to be performing some queries on that data, and we're going to be writing those query results back to the gold or aggregated area of our data lake as partitioned Apache Parquet format files. And again, we have a DAG to do that. We don't have to run any commands ourselves or use the UI. We're going to use a DAG which has been created for that purpose. So let's open DAG 4 and take a look at it. And I'll switch over to the graph view. So we have two create table as statements. We're going to be executing those using Amazon Athena. Those create table as statements are going to be querying data on 6 out of the 7 tables of data that we extracted from our 3 data sources. So it's going to be doing a join across 6 tables. It's going to be performing some basic SQL functions on that data. And it's going to be then writing that data back to the gold or aggregated section of our data lake. And we're going to be partitioning that data. So in the first case, we're going to be partitioning that data by both category group and category name, assuming that a lot of the queries that our end users will be writing will be based on a particular category of tickets that are bought and sold. We're also going to be partitioning that data by year and month. So the assumption is that our end users will be querying that data by the year and the month that the sales transactions took place. A typical monthly sales report, a typical year-to-date sales report. So we're going to be writing the same query, but we're going to be writing that data back 2 different ways into the gold or aggregated area of our data lake. One partitioned by category and the other one partitioned by date. So sales by category, sales by date. And then when we're all done, we'll go ahead and run a query just to make sure that we can actually query that data. So the assumption is that our data analysts and data scientists, in addition to the refined or silver data, can use those aggregated data sets for their analysis. So we want to make sure that those 2 different data sets are actually available and they're queryable. So after we create the 2 data sets, the other task that we'll run, the third task that we'll run, will actually query the partition data by date to make sure that we can execute a query against it as part of our DAG. And then if that completes successfully, we'll go ahead and list the tables just to make sure that we in fact have all the tables that we expected in our AWS Glue Data Catalog. So let me start this DAG. So we'll go ahead and trigger the DAG. So that DAG has been triggered. Go back to the graph view to keep an eye on it. And while this is running, let me just switch back to my ID and I'll show you the 4th DAG. Again, all these DAGs are available in the open source GitHub repository. So this DAG's a little different, and we could have done this a couple different ways. The way I've done is I've actually put the SQL query, the create table as statement within the DAG. We could have created a separate SQL file and then called that SQL file as part of the DAG and brought that into the DAG, and it would have made this a little more succinct, a little less code. But I chose to put those right in here so they're available if you download this. So we have 3 SQL statements. We have aggregated ticket sales by category, which I mentioned, and we have aggregated ticket sales by date. I also have a third query, which is going to do a simple select statement, and we're going to use the aggregated ticket sales by category. So I just want to make sure that after I write this data back to our data lake and the schema metadata information is written back to our AWS Glue Data Catalog, that I am able to query it. Again, if you're not familiar with the create table as statements using Amazon Athena or Presto, you're looking at those on the screen. First off, we have the format. We are writing the data back as Parquet, as I mentioned. We're using snappy compression. I have the external location. So again, the ticket gold subdirectory. We're going to create a ticket sales by category and a ticket sales by date subdirectory within the ticket gold area of our data lake to write that data back. In this case, I'm partitioning the data by category group, cat group, and category name, cat name. So those are 2 of the columns in our data, and I'm using those to partition the data by, and when this DAG finishes, I'll show you what that looks like. I'm also using a bucket by, and I'm using a bucket of 1. What I want to do when I write this data back, I want to write all the data back as a single Parquet file. Next, we have the select statement. So the select statement will return a result back to Amazon Athena. That result is what is actually getting written back to Amazon S3 as partitioned Apache Parquet. So you can see the select statement on my screen. We're joining the sales table with the listings, users, events, and dates tables. We're performing some fairly basic SQL functions on that, rounding some of the numbers off, making sure that they're cast correctly, concatenating the first and last names. That result set is then being written back to Amazon S3. First, the result set is being written back partitioned by category group and category name. And then we're performing the exact same query, the only difference being we're partitioning it by year and month. And then lastly, we have the third query. The DAG itself uses the AWS Athena operator. So we have 3 AWS Athena operator tasks, 1 for each of the queries, the 2 CTAS queries, and then the normal SQL statement to validate that we can read that data back in that we've written to Amazon S3. And then finally a batch operator, again, which just lists all of the tables in our AWS Glue Data Catalog, which start with the aggregated or AGG underscore prefix. And I would expect to have 2 tables. If we switch back over, it looks like DAG number 4 completed successfully. Again, following the same pattern, let's take a look at the last task, which should list those tables for us. I would expect to see 2 new tables, and in fact we do. So aggregated ticket sales by category and aggregated ticket sales by date. So it looks like that worked. Let's switch back over to our AWS Glue Data Catalog. You can remember that we had 21 tables after we completed DAG 3. So 7 source, 7 raw, 7 refined. Let's remove this classification. So now I have 23 tables. So in addition to my 7 source, 7 raw, and 7 refined tables, I have 2 aggregated tables. So we can take a look at that. We can see that the underlying location is in fact in our Amazon S3 bucket within the ticket gold ticket sales by date subdirectory or key prefix. We can see that we have snappy compression. And if we scroll down a little farther, we can see the schema. So this is the schema of the result set that was returned from the query and then written to Amazon S3 as partitioned Apache Parquet format. And you can see here in this case, since this was by sales date and we partitioned by year and month, we can also see what the partition keys are. So we see those here. Also, if we go up here and we view the partitions, we do see 12 partitions. So this particular data set has sales data for 1 year, the year 2020, and for 12 months, January through December. Instead of having a numeric value for the months, we have a 3-letter string. We could have taken care of that with ETL, not a big deal. Still works just fine as a partition. So we have an integer as a partition, and then we have a varchar or string as our partition. When we write our queries, we're able to say select sales where year equals 2020 and month equals June, and we'll get only the sales results back for that month. Looks like that worked. Everything worked there. Let's take one last look at our S3 bucket. I'll go back out to the tickets prefix key or subdirectory. We do in fact now have a bronze, silver, and gold section of our data lake. If we go into the gold section or subdirectory, we have 2 subdirectories or key prefixes within that gold prefix. We have ticket sales by category and ticket sales by date. If we go into one of these, we see our partitions. I'm in the ticket sales by category. If you remember, I said we were going to partition by category group and category name, and that's what I see here. So the parent partition is category group. In this case, we have concerts and shows. If I go into shows, the category group is shows, I have 3 category name partitions. So I have musicals, operas, and plays. And we can go into one of those. So if I go into here, I would expect to see one Apache Parquet format file. If you remember, I said as part of my create table or CTAS query, I used bucketing and I did a bucket of 1, which means that I coalesced all those individual Apache Parquet format files back into a single file. One of the reasons I did that, just to show you how bucketing works, but also the lesser the number of files we need to read in as part of our query, the faster and more efficient that query is going to be. So in this case, within the shows category group, within the opera category name, I only have 1 Apache Parquet format. So if I write a SQL query that says where cat group or category group equals shows and category name or cat name equals opera, I'm only going to turn the data within that subpartition, within that parent-child partition of shows opera. And in this case, at least for right now, I only have 1 Apache Parquet file, so it's only this 297 kilobytes of data that it should scan, which will make the query much more efficient. So those are the 4 DAGs. Those 4 DAGs correspond to the 4 steps that I outlined in our architectural diagram to build our data lake. So we're done. Our data lake is built. We could go ahead and start querying that data. The data analysts and data scientists, the consumers of our data lake, can use any of the data in the data lake, the bronze, silver, or gold data. Probably what's most common is they would use the refined or silver data if they know how to write their own queries and join those individual tables. In addition to that, it can use the aggregated or gold data sets, which have really been optimized. They're partitioned, they're compressed, they're written in Apache Parquet. They can use those to perform additional analysis. They can further perform ETL on those to prepare those for machine learning, or they could use those data sets directly within their business intelligence or visualization tools, things like Tableau or QuickSight or Looker. They could use those data sets correctly to create dashboards and visualizations based on that ticket sales data using those aggregated data sets. So that completes our demonstration. One last optional part. Let me switch back over to our Airflow UI. What Airflow does for us is allows us to separate our concerns, create individual tasks within individual DAGs, which all together make up a data ops workflow. So in this case, we went from cleaning up an existing environment to extracting metadata and schema information from data sources. We then took that information, we wrote it into our data lake. We then took that raw data and we refined it, wrote it back to our data lake and cataloged it. We then took that refined data, again, we refined it, we aggregated it, we joined it, we performed some additional SQL functions on it, and then we wrote that data back to the aggregated or gold area of our data lake and we cataloged it. And we were able to do that using individual DAGs, which together made up that entire end-to-end workflow. Running those individual DAGs may be useful depending on particular workflow that you've constructed. There may also be an advantage to running all of those DAGs sequentially by using a single DAG. So that's what I've done here. This single DAG runs each one of those 5 DAGs sequentially. Instead of running 5 DAGs, waiting for DAG 1 to finish, then run DAG 2, then run DAG 3, and then run DAG 4, you can write a DAG which calls other DAGs. So let me open this. We're using what's known as the trigger DAG run operator. and we have a series of 5 of those that correspond to our 5 DAGs. So I'm calling DAG 0, then DAG 1, then DAG 2, then DAG 3, DAG 4, and you can see that I have those in a sequential format. So instead of in parallel, because they are dependent on one another, right? I want to clean up the environment before I start my demo. I want to be able to extract the metadata and schema information before I use that schema metadata information to extract the data from my data sources. I then want to be able to use that raw data. I want to be able to refine that data, write that data back to my data lake, and then finally I want to take that refined data, aggregate it, and then again write that back to my data lake. So there's dependency on each previous DAG, so therefore I want to run those sequentially. This DAG runs each one of the other 5 DAGs sequentially. So all I have to do is kick this single DAG off and it will run all of these jobs. It will clean up my environment. It will take a look at my database to extract that schema metadata information. It will then extract the raw data, put it into my data lake. It will then refine that data. And finally, it will aggregate that data and write that data into the gold area of my data lake. When I'm all done, I'll have the same results as what we went through over the course of the demonstration that we just ran through. So let me switch over to the DAG runs UI. We can see all of the DAGs that we've previously run. If we scroll down here, we can see run DAG 0 through 04. We can see after that the DAG 0, then DAG 1, then DAG 2, then DAG 3, then DAG 4 were kicked off in order. This DAG triggered all 5 of these other DAGs. This DAG started at 2204 and finished at 2223. In about 19 minutes, we had constructed our entire data lake using that one DAG by just clicking one button. So that's a way in which you can be more efficient with Airflow, is using one DAG to kick off multiple DAGs. Thank you very much for your time. That's going to end our demonstration.